despite being scalars. Somehow, I believe that a lot of our students might still find the concept of distance or average speed a little bit trickier than they thought. And that's a bit partly because the way we define the average speed. So let's look into this problem about the definition of average speed. So hopefully once we figure out this whole problem, and you guys will see how important it is for us to know very well about the definition of a physical quantity. All right, let's get started. So the scenario is actually pretty straightforward. All right, this guy drives from his home to the grocery store. And let's say, just to be simple, we assume that he drives straight ahead to the grocery store and a speed he had on the way there is a constant speed, and let's say it's v1. By constant speed, I mean the speed is going to be the same the whole time. Say, I don't know, maybe 70 miles per hour. Right? I don't know if it's that realistic, but let's just make the math a bit simpler. Assuming that the path is straight from home to the grocery store and the speed along the whole path is constant. The value is v1. Now, for some reason, when he gets to the grocery store, he spent no time and decided to drive straight back from the store back home. And the speed on the way back will be, of course, most likely a different speed, right? And there's no reason to have the same speed as before. So let's call it the speed on the way back from the home, from the grocery store to the home, will be a constant speed v2. So the question is, what do you think will be the average speed of his whole trip, right? So we're not concerned just the trip on the way out and coming back. Let's take the whole trip going out and coming back, right? And all we have to do is to refer to the definition of the average speed. All right, so let's go ahead and write it down. So average speed for the whole trip must be the corresponding distance for the whole trip divided by the total time taken for the whole trip. But the tricky part of this problem is that we don't have the distance, right? We don't know how far the home is away from the grocery store. But here's a little trick. If we think that the problem is not providing something that we actually kind of need for our calculation, we can assume whatever we need, but you know that at the end of the day, somehow the math will work out magically that our answer should not depend on something that we assumed, since that was never given by the problem. All right? So in this case, let's assume that the straight line distance between the home and grocery store is d. Now, the total distance for the whole trip, right, going from the home to the grocery store and coming back, must be 2 times d. All right, so now the question is, how do we compute the time? And of course, you can assume the time taken for the first part of the motion from the home to the grocery store is t sub 1, just like we have the speed v sub 1, right? And the second part will have the time to be t sub 2, right? But then we end up assuming too many unknown quantities. We already have the unknown d, right? We hope that later on d will somehow magically disappear. So let's try not to bring in more unknown quantities. So let's ask ourselves, is there a way we can relate time taken from the home to the grocery store to something that we either already assumed or we were given by the problem. I'm sure you can see that the time taken from the home to the grocery store must be the distance, which is d, right? Divided by the speed on the way from home to the grocery store, v1. So d divided by v1 is the time taken to go from the home to the store. So that's the time for the first part of the trip. Now for the returning, well, we can do the same thing, right? Just go ahead and divide the distance d by the v2 because we assume that this guy drives straight back along the same route, and it's going to be a straight path, right? So again, let's just make the math as simple as it can be because that's not the focus of the problem, right? Anyway, so now we're looking at a complex fraction. Right? If you remember what that means back in algebra, you know what to do about simplifying this complex fractional expression. Okay, so now feel free to pause the video for maybe a minute or two to work this out. Welcome back. All right, so now let me welcome back. Now let me show you the detailed work of simplifying this complex fraction. All right, so well, first there are more than one way to do it. So in this case, let me just show you one way and feel free to try whatever method that you feel more comfortable with. But all I want to make sure is you know that in this case, our goal is to simplify this complex fraction as much as we can. And remember that we're not supposed to have our final answer depending on the d, right? So that's another thing to keep in mind. So in this case, how about we first focus on the denominators? All right, so we have two fractions in the denominator. So how about we add them up? Well, the problem is the denominator v1 and v2, they're not necessarily the same, right? So now the question is, how do we add up two fractions with different denominators? Yes, we can do common denominator. All right, so in this case, let's go ahead and write the first fraction in the denominator, d times v2 over v1 times v2. And the same thing that we can do to the second fraction here, but instead of multiplying v2, we're going to multiply d with v1 on the numerator, and on the bottom we have v2 times v1. So I hope that you see what happened here. It is we use the property of a fraction, right, which says that if we multiply the same non-zero number with both the numerator and denominator of any fraction, the fraction stays the same. In this case, we decide to multiply v2 to the numerator and denominator of the first fraction, and multiplying v1 to the numerator and denominator of the second fraction is to make sure that at the end of the day, we have the same denominator for those two fractions, right? They both read v1 times v2. So now we're ready to add up these two fractions in the denominator. Okay, so we can put d times v1. Actually, you know what? It doesn't matter. We can go with the v2 here since that was the first numerator. D times v2 plus d times v1 over v1 times v2. Okay. Now, just to make our life a little bit easier, let's go ahead and fact out the d here and there. All right. So what we're going to do is we put 2D over, here we have D factored out, so you have parentheses, V, oh, sorry, there's a typo here. It should be a V1. I'll put V1 plus V2 because the order doesn't matter for the addition, right? Over V1 times V2. All right, so now we're gonna record a very important property of division. Right? If you divide anything by a fraction, it's equivalent to multiplying its reciprocal. Right? So now we're gonna have 2D times the reciprocal of this guy, which is V1 times V2 over D, open parentheses, V1 plus V2, close parentheses. And I hope you see that here. The D's cancel as we expected, right? So at the end of the day, you got 2 times V1, V2 over V1 plus V2. All right, so let's put this guy here as our final answer. 2V1, V2 over V1 plus V2. Okay, so it looks like that we're done. Well, yes, but for the math part. But that's definitely not the whole point of the problem. Let's make some sense of this answer, because this just looks odd, right? Think about that. If you have two different speeds, right, V1 and V2, if you were to average them, what do you think would be the average speed? And most people would say, well, it better be V1 plus V2 over 2, right? No, that's not the case. Now, how do I make sense of it? Okay, here's something we can do to help us understand our result a bit better. All right, let's just try some numbers. Let's say V1 is 10 meters per second. I know it doesn't make sense that why would someone drive at such a low speed. But anyways, just want to make the number a bit easier for us to calculate, or it doesn't have to be that realistic. As long as you see the whole concept that the average speed here is not as simple as you think it is. Anyway, so V1 is 10, V2 is say 20 meters per second. All right, so according to our result, the average speed is then 2 times V1, which is 10. V2 is 20, right? Divided by V1 plus V2, so 10 plus 20. All right, so we're looking at 400 divided by 30. So 40 over 3, which is approximately 13.3 meters per second. All right, so now, very important. This is definitely not the regular average you take based off the two numbers, 10 and 20, right? This is not the same as 10 plus 20 over 2, which, as you know, is 15. But what's more interesting is the average we get for this problem is actually less than 15. Now, how do we understand it? Well, here's a pretty easy way. It turns out that here the two speed, V1 and V2, are not weighted the same. And this is just like, say if you take 10 quizzes throughout the whole semester. You've aced 9 of them. You only failed 1 quiz. So you get an F versus 9 A's. And somehow your teacher decides to give you an average quiz grade, which is around maybe a C. And I'm sure that you won't be happy about that, right? Because it's just not fair, right? So you've been getting straight A's, right? But you only screw up 1 quiz, it might just be some uncontrollable, situation, right? So you might expect your quiz grade to be super close to an A, even though it's not, exactly an A, but you're expecting maybe at least an A minus, right? The worst case scenarios will be a B or B plus, right? Getting a C is definitely not fair. In this case, it's very similar. So this guy was moving at a low speed, right, 10 meters per second, and later he moves at a higher speed, but of course, he spent twice as much time, right, at the lower speed. Just like, if you were to spend more time with a higher grade, your average grade should be closer to the grade that you spend with the most of the time, right? The same thing here. This guy spent more time with the lower speed, which is 10 meters per second, and that's why the average speed should be closer to the speed that he spent the most time with, right, which is the lower speed. And that's why the average speed is not exactly 15, which is exactly between the 10 and 20. It will be closer to the lower speed because this guy spent more time on it. All right. But don't get me wrong. I'm not saying that you have to know for some reason that here we calculate average speed, but it turns out to be the weighted average of the two numbers, right? You don't have to do that. If we're lucky, we have a pretty good, intuitive explanation of why the result that we calculate takes this, funny form. But you see that all we have to do to figure out this, weird result is to blindly follow the definition of the average velocity. So later on, it turns out that whenever it comes to the definition of a physical quantity, we have to take it very seriously, right? So the definition of the physical quantity has to be true no matter what. So whenever you're thinking about calculating something, if like a test problem asking you about something and it turns out to be a particular physical quantity that you definitely know what the definition is, and I will say that go with the definition. You can never be wrong. If that doesn't work out, try something else. But you first have to try the definition because that's what we care the most in physics.